Swayam Prabha. Digital India. Educated India.
Welcome back to week 2 of this NPTEL course on muffler acoustics. So, all this while in the last week which was our introductory week, we talked about some basic or simple concepts on wave propagation, one dimensional wave propagation and ducts, some transient solutions and derivation of the one dimensional acoustic wave equation which is valid in ducts. So, and then we of course briefly touched upon the effects of mean flow on ducts or on harmonic plane waves that propagate within an infinite duct. We also I guess talked about a little bit about boundary conditions, rigid wall conditions and the open end boundary conditions and all that, impedance concepts. Well, in real world however, waves are rarely one dimensional except of course in ducts, which is obviously our focus of this course, very much related to mufflers. So, even within ducts there exists a certain frequency based on the cross section of the duct, whether it is a rectangular cross section or a circular cross section. There exists an upper bound or upper frequency beyond which wave propagation can no longer be considered planar. So, 3 dimensional effects begin to show up. So, what it means? So, let us consider a duct. Let me draw a nice photo for you. So, here you have your this thing. So, the idea is that here you have planar waves. So, basically at any point here, anywhere waves have the same phase, What it means is basically any point you pick on this plane has the same magnitude, same value. So, it is basically a plane surface. Now, when 3D effects, by the way, this is say the z direction, this is say x, this is the y direction. We are considering origin to be say somewhere here 0 0 0, which is your x, y and z. So, this is a rectangular duct. Okay. As I was saying that the only dependence is along the z direction, that is if you consider another plane, this is let us say this is at z is equal to L1, this would be at z is equal to L2. So, this is another planar wave front. So, the values would be different from what you get from z is equal to L1. So, the idea is that the only dependence is now on the z direction, that is if z is changing then the values will also change. But like I said, there is a difference between this idealistic or theoretical world and the actual the realistic environment. In real world, beyond a certain frequency, 3 dimensional effects will begin to show up, that is to say the wave propagation or the acoustic say the pressure value P tilde will no longer just be P z, it will be P of x, y and z, and of course, we assume time harmonicity. So, the idea is that the waves will no longer propagate or depend only on the z, they will also depend, their propagation will also depend on the x and y values. So, what it means is that this surface will no longer be a planar surface, it would probably have some sort of a variation across this thing. So, we will probably have a look at some nice mode shape patterns. I will draw some nice schematics to drive home the concepts of how the pressure varies across a rectangular cross section, or for that matter a circular cross section, and for that matter elliptical cross sections, because mufflers are also elliptical in shape, although it is more complicated. Now, ducts can be subject to rigid wall condition or subject to lining condition. So, the purpose of this today's lecture is to present to you all the the set of consolidated lectures 3 to 5 which initially I would begin with a derivation of the acoustic wave equation in a Cartesian coordinate system, but involving the other two coordinates x and y, and z of course is there. So, that would be the 3-dimensional wave equation, but in a stationary medium, and that will be valid for rectangular ducts once we implement the appropriate boundary condition, whether it is a rigid wall condition or open end condition. Open end generally is not used, we use impedance condition, but when this set of lectures we stick only to hard wall ducts, that is normal velocity is 0. We will talk about the line ducts later in the probably in the last few weeks or last few lectures of this course, line ducts. So, we will worry only about the rigid walled ducts. Now, let me just begin to derive the 3-dimensional wave equation in the Cartesian coordinates, and then we can possibly add a mean flow term to account to understand all the things pertaining to a rectangular duct, concepts of cut on frequency and all that, before we move on to the circular duct, which is our very important topic that will help us in the later parts of the course. Let me draw a system here, system something like this kind of a thing. So, this is nothing but a cubical volume element, of in a fluid, and we see, let me use another color, and let me actually first also draw the conventions. So, this can be your say the y direction, this can be your x direction, and this can be your z direction. Along the z and y phase, we have the flow that enters here, the one that leaves here. Note that this is your delta y, this is your delta z. Similarly, this is your delta x, and like this. Okay. This particular area is delta x into delta y, delta x into delta y. So, what we get is your delta z into delta y, okay, area into the density, area into the, well, we are interested in knowing the amount of fluid that enters this phase per unit time. So, if you multiply this by the velocity, say u is the velocity along the x direction. So, here I must also introduce certain things. U is along x, v tilde is along y, and w tilde is along z, and p tilde is depend upon x, y and z. So, velocity into the area will give you meter cube per second, or the volume flow rate. Now, if you want to get the mass flow rate, you need to multiply this by the density rho. So, all the terms are evaluated at at x is equal to let us say it is evaluated at x. Okay. Now, what do we do after this? We multiply. Now, we also need to worry about the flux that goes from the other phase. So, if you are considering this as x, this is x plus delta x. So, delta z into delta y into u tilde rho, actually this can be just the velocity. We will do linearization later. So, and we will do the linearization part later. This is the velocity at x plus delta x. Okay. This is the total amount of fluid that enters from the left hand side on the from the delta z and delta y phase, or z y phase, and the amount of fluid that goes in from the opposite side is delta z into delta u into u rho at x plus delta x. Now, what happens to the fluid that comes from the phase z x, that is your like this, and the one that goes away is like this. So, this is your delta z into delta x into v. Along the y direction, it is velocity is v and rho. So, this is at y, and this is rho v delta z delta x at y plus delta y. Okay. And what about the flux that goes along the or travels along the z direction? So, let me use yet another color to simplify things. So, one that enters the volume is from this, from the bottom face, from the bottom face it enters it from this face, that is your rho times w delta x into delta y at z, rho w delta x delta y at z plus delta z. Okay. So, basically by drawing this figure, what we have done is that we have identified in the small control volume, cubical control volume, the fluxes that enter from different faces and the fluxes that enter exit from the opposite phase. So, naturally what the next step is basically to balance out this thing. We are heading towards what is known as conservation of mass, we are headed towards that. So, what is the difference now? Delta y into delta z into rho u x minus delta y into delta z into rho u x plus delta x. This is the difference of the mass that enters here and the mass that leaves here. So, difference of that will give you the net amount of mass that exits the system. Now, if you have a similar thing, if you have the mass that goes into the phase here and leaves here, so what is that? Delta z and into delta x into rho v at y, I guess y, isn't it, and minus delta z into delta x into rho v by y plus delta y. Okay. So, that is the difference. Now, we have another thing which is the mass that enters from the bottom and leaves from the top face. So, delta x into delta y, remember, because we are dealing with mass that flux velocity along the z direction, delta z would not be there. We have other terms, delta x and delta y into rho w z plus delta z. Okay. The difference of the fluxes, that is equal to. So, this is what have we done basically? We have figured out the net mass inflow through surface of delta v. So, this is the net mass influx. The difference is then equal to the net mass that goes away, that is your del del t into rho times. So, this is the really the mass that this is the volume delta x into delta y into delta z, volume times density kg per meter cube into meter cube, that will give you kg, right. So, this should be, if you take the derivative of that, that is basically your kg per meter cube into meter cube. So, what we get by this is that we get kg. So, to temporal rate of change. So, this is then equal to net mass increase inside delta v. This is a mathematical rendition of the most one of the most fundamental laws, that whatever difference of mass we are seeing that comes inside and goes outside, the sum total of the differences must be equal to the net change of mass within the control volume delta v. Delta v is nothing but delta x into delta y into delta z, this one. So, so volume times density is the total mass at any instant net mass within that control volume. So, time rate of change of that is equal to the net mass influx through different surfaces of delta V. So, that is what we get, net mass difference. So, this is basically what we get. Of course, delta x, delta y, delta z, these dimensions are fixed and rho can be changing. Density, this might change, especially in acoustics we are having a small perturbation thing. So, this is what would produce the acoustic effect. So, now let us basically simplify this entire expression. Note that if we divide throughout by delta x, delta y, delta z, what will we get? We will get in the first term delta y and delta z will sort of cancel, and we will get at x minus rho u x plus delta x divided by delta x and plus rho v at y minus rho v at y plus delta y divided by delta y and rho w at z minus rho w at z plus delta z divide by delta z, we get this. Now, this is clearly this is nothing but the partial derivative with respect to the following. So, let me use another slide, and what we will get is basically del rho u by del x. So, clearly if we take the limit that delta x is tending to 0, limit delta y is tending to 0 and limit delta z tends to 0, we will get or actually there should be, I made a small mistake here. So, this would be nothing but minus of each term, because definition of derivative. So, eventually one form of the continuity equation. So, we are dealing with the conservation of mass. So, we will get the continuity equation, or so, we will basically get these two, equation 1, or same another form, let me call this equation 1a and 1b. So, the 1b is the kind of a more compact form, and this is the fully expanded out form. So, del del T of rho plus your divergence of rho u, del del T of rho plus divergence of the product del u. So, u actually, let me make it somewhat different from this thing, u, writing it manually bold, where u is your, where u is nothing but u v w. So, you see it is a divergence operator, this guy is a divergence operator. So, rho u is a vector, because u is a vector defined like I have done here, and divergence operator operates upon this vector to get back a scalar product. So, basically we are adding two quantities. Now, we can very quickly put the isentropicity condition here, but I guess we will probably wait till the derivation of the momentum equation. So, in fact, we will use 1a form, the form 1a to derive the more simplified form of the momentum equation. But before we go ahead, let me just point out to you guys that the same thing can also be obtained through an integral approach. Right now, we took a control volume thing and figured out the partial derivatives and all that. But if we were to do it in a integral, derive the integral form of the continuity equation using the same physical principle, that time rate of increase in the mass delta V is equal to the net mass inflow through surface S, and get the integral forms of such things instead of differential forms, we will pretty much arrive at the same thing. So, this is a very important concept. So, I will probably not go into that now, but I guess just leave it here and go to the derivation of the momentum equation. So, now what we are going to do is that we are heading towards the momentum equation. So, this is basically your balance of forces. So, let us consider again our cubical control volume, and let us define a coordinate system which is pretty much the same as was before. So, x, y, x along this direction, y along this direction, and z along this direction. So, sorry. So, basically we consider the forces. Let me draw the cube, the unit cube of course along this direction, and talk in terms with reference to the faces. So, if you have your x like this, z like this, and y like this, let us say identify the faces. Now, we need to first let us be systematic and identify the forces that act along each direction. So, here the difference between momentum and continuity equation is that now we are in momentum, we are trying to balance the forces. So, we will basically end up with not one but three equations, one for the balance of forces along the either of the directions, x direction, y direction, and the z direction. Let us consider now the x direction. So, if we name it as say A, B, C, the inside vertex is D, E, this one is F, G, H. So, the face A, D, H, E, the face A, D, H, E, the force that or the pressure that acts along this direction is the or the force that acts along this direction is pressure P. Let us work with P or the total pressure. So, P into your delta y is nothing but this one, and delta z is this one, and delta x is this. So, P into delta y into delta z at x is equal to x or x naught, whatever you want to say. Let us call it x, minus P times delta y into delta z into x plus delta x. So, the difference of the force is equal to what? This is the difference. So, this is pressure P into the area that will give you force that acts on the face A, D, H, E, and this is the thing that acts on the face B, C, G, F. So, the difference of the two forces will give you the net resultant force, and that must be sort of balanced by the momentum. So, on your left face is left, and this is left face, this is the right face, and you can consider this is the bottom face, the top face, and this is the front face and the back face. So, we are working with left and right faces as far as x direction is concerned. So, what is the momentum that enters force due to the momentum flux? Because momentum is carried by the moving fluid as it goes through delta V. So, the momentum inflow into the control volume, that also accounts for the force. The force due to momentum influx is then basically given by the one that acts through this A, D, H, E phase is rho u, and your area is delta y into delta z like before at x. Now, area times velocity, area times velocity is your meter cube by second, and this is your kg per meter cube. So, kg per meter cube times meter by second, and this is your meter cube by second. So, basically again like we did in the last week, we basically this has dimensions of force kg meter by second square. So, this is your q dot kind of a thing, volume flow rate, and and this is the density and the area, density which kind of conveys the mass times this thing. So, in a way if you group this particular term together, rho times this thing and u is here. So, it is like your mass, this will give you your mass m dot times velocity. So, naturally mu is the momentum, and if you since m dot is with respect to time, so per second will come. So, that is why you are getting the units of force. So, basically this denotes force. So, I would basically club this thing as the following: rho u times this minus rho u into delta y into delta z at x plus delta x. So, we get this kind of a thing. Now, the one that leaves outside. What do we do now with this particular thing? what we will see is that basically these are the forces that act on the faces A, D, H, E. So, we need to basically add this term and subtract this term or this term, because minus sign anyways is already there. So, this is the force that acts in the other direction. So, what it would mean is that your rho u times u into delta y into delta z at x minus rho u into u times delta y into delta z at x plus delta x. So, this is the like I said, force carried by the momentum influx and the force acting in the opposite direction due to the momentum outflux, and the difference, the pressure, they act on the opposite direction on opposite faces. So, you get your p times delta y into delta z at x minus p times delta y into delta z at x plus delta x. Okay. So, this is the net force, and what is it equal to? So, this is equal to the net change of momentum inside the control volume. So, your delta x into rho times the volume is your mass. So, mass into the velocity along the x direction. Remember, u was, remember from slide 3, u was the velocity along the x direction. So, this underlying thing is your kg, density times volume, and this is your meter by second. So, kg into meter by second. So, basically this gives you your mu term, like your momentum, and time rate of change of momentum is your force. So, basically what we do is now we divide throughout by the unit volume, that is your delta x, delta y into delta z, product of that. So, and we simplify the terms a bit. So, we will get minus del p of del x minus del rho u square this thing. So, up till that there is no problem, but there are a few more terms which we didn't mention now, but it is true that the momentum is carried along the x direction, momentum flux by these fluxes, but then there is also your force that along the x direction that is carried due to the, because of some component along the x direction by the momentum influx through each of the faces from the front face and the back face, as well as from the bottom face and the top face. So, you get basically all those terms. Let us see how we get it. So, basically the component of the momentum along the x direction due to the force, due to the influx along perpendicular to the page, that is through the faces A, E, F, B, is basically, we will come back to this the last slide, A, E, F, B is given by rho u v times delta x into delta z at y, and similarly along the face C, G, H, D, C, G, H, D, we will be getting the force, that is your rho u times v into delta x delta z at y plus delta y. Similarly, the force due to the momentum influx top faces is basically rho times u, this component will always be there, now w, and now you have your delta x and delta y. So, this will be your z, and rho u times w into delta x into delta y at z plus delta z. So, the face is, for the bottom term, the face is A, B, C, D, isn't it? A, B, C, D, and the top face is your E, F, G, H, E, F, G, H. Well, the idea is, how are we getting all these things? Because again the same thing, the momentum here we are basically, the momentum influx is nothing but it has the dimensions of q dot, but this is along the your y direction, that is this direction. So, because your area times the velocity, and so if you multiply this by the density, you will get kg or mass along the y direction, and that mass into the velocity will basically give you the momentum along the x direction, u being the velocity along that direction. Now, again what we need to do is that the idea is fairly simple. we need to add those relevant terms in here. What I will do is that probably get rid of this part just for now and put this thing at the bottom. So, rho u delta x, delta y, delta z, and to make some space for these terms. So, I will directly do the simplification, or probably I can sort of write rho u into v into delta x, delta y, z, x, delta, this is your delta delta z and delta z, and this is your y term, y plus delta y at z plus delta z. So, now if you divide throughout by delta x, delta y, delta z, and simplify the expressions, we will get the following: minus rho u v times your y and rho u w z. We will get this. If we were to simplify this further, probably what we could do is that we could write this a bit more compactly: rho u times t plus rho u square times x plus rho u v times y and rho u w times z plus p x is equal to 0. Now, remember, these suffixes signify differentiation with respect to that particular coordinate. So, when I am writing, when I am writing something like this, it would mean the following, and similarly for y and z and all that kind of a thing. Now, what do we do now? We have to basically, just like we did for the one dimensional equation, we will have to cleverly group terms. So, let me expand this guy, these terms out. So, this is like this, and rho u x into u I can write, plus rho u times u x I can write, and then rho v times u, let me club this thing together, and u y, well, and here you have your rho w times derivative with respect to z and u So, you get this plus of course, your P x is equal to 0, you get this particular thing. Now, we have to clearly identify terms, this of course is plus, this of course is plus. Now, if we take u common here, u is common here, u is common in this term as well here and as well as here. So, this is nothing but we get basically your continuity equation, rho t plus rho u whole x plus rho v y plus rho w z, entire thing multiplied into u plus all the other terms is equal to 0. So, this clearly this term cancels away. Why? Because of your continuity equation that we derived here. Remember, I said just a while back that 1a is the form, or probably 1b, whatever it is, we will use, and we are indeed using that form. So, basically the remaining terms, what are those then? Let me write it down. So, rho u t, rho u into u x plus your rho v into u y and your rho w into u z plus your P x is equal to 0. So, this also can be written as u t u times u x plus v times u y and w times u z plus P x is equal to 0. So, P x is nothing but del del x of P, like we have been talking about. So, a more compact way, remember now your ux would mean del del x of u and uy would mean del del y of u and so on. This is basically a vector equation in the sense that all your u v's they are all vectors. So, perhaps a more compact way of writing this term is then your rho times, remember this operator is nothing but your del del t plus u times del del x and v times del del y and w times del del z. This whole thing is acting on your u term u. This is basically your thing that acts upon this. So there this particular term is u, and your here you have your del del x of p equal to 0. Okay. So, the compact way of writing the above equation is also basically rho times d dt of u, where d dt is this entire operator, plus p x equals 0. So, either of that is your momentum equation along the x direction. Similarly, after this little bit of rigorous thing, we will get the momentum equations along the y direction as d dt of v plus p y is equal to 0, and along the z direction it is given by p z. Now, actually this would be 0, but if you consider gravity, like I said, it will be minus rho naught times g, because this is the body force, remember, but we will probably ignore it in this course. So, we will set these things to 0. So, basically another thing that we must point out here, that we are not actually considering the viscous terms at all. We are considering inviscid equations, because we are not considering attenuation due to the viscosity or damping in air. We are considering only the linear only the Euler equations, that is 0 viscosity in viscid flows, and once we get your momentum equations, then we will probably linearize it to get the linearized Euler equation in case flow is there, and then from that we can combine it to get your Helmholtz equation or the wave equation. Let us see how we go about it. So, this is your one equation, this is your another equation, and this is, let me call it, this as 2a, 2b, 3 and 4. Let us not consider the mean flow for a while, let us work only with stationary flows. Okay. So, we will probably need to have a closer look at this thing. So, if you remember our last discussions, when we began on the process of linearization. So, right now we have not done any linearization, they are just the equations, Euler equations, because inviscid flows is there. What we need to do in the context of acoustics or small signal equations, basically your start to linearize the term. So, basically we immediately recognize V or U, V, W, they are all small quantities, there is no mean flow, U naught or capital U naught is 0, that is no flow along the x direction, and this term goes away, because when you linearize it you get U is equal to U naught plus U tilde, V is equal to V tilde and W is equal to W tilde. This guy is 0, now we will assume that, and these two terms would also be gone, and obviously this term also, product of two second order quantities. We have seen that derivative does not, by non-dimensional arguments, we have seen in the last lecture that it does not matter, they are also very small quantity. What essentially we are left with, let me use another slide, is basically a rho times del del t of u plus or u tilde, and P of course is also your ambient pressure times this, and we assume that this particular term, this is 0, that is there is no gradient of the ambient pressure is what it is, it is constant, and rho naught of course is rho naught plus rho tilde. So, rho tilde again, you know, it will be a second order quantity. Rho tilde into delta T of u tilde, that will be a smaller quantity, we sort of neglected. So, rho naught times this thing is equal to 0. Similarly, along the y direction, these are perhaps the most simplified cases that you will come across. So, we get this. Okay. So, this is your set of linearized momentum equations or linearized Euler equations. What about the continuity equation? You know, remember we had a thing, you know, this one. So, the arguments are pretty much like what we did in the last week for the one dimensional test case. In one dimensional test case, of course, this guy was not there, this guy was not there, right, but now they are there. So, we can easily show that, you know, rho is again your rho naught plus rho tilde, V and W are nothing but V naught, V tilde and W tilde. This flow is considered only along the z direction or x direction, let us say. When we do all those things, we will get the following equation. So, let me write it somewhere here. Your this would become your rho tilde times this plus rho naught into delta u, where u is your nothing but the vector, is equal to 0. So, in an expanded out form, the continuity equation will be equals 0. Okay. So, this is what it is going to be. So, we have your, you know, three equations. So, let me call this as 5, 6, 7 and 8, 5 to 8. So, these are the equations that constitute equations for getting the wave equation. Now, we will also immediately use isentropicity condition. Now, recall from the last week's lectures, P tilde by rho tilde is nothing but C naught square, sound speed, small signal thing. So, rho tilde then would become P tilde by C naught square. Okay. So, what we need to do now? We need to substitute this guy here to get your this thing okay. So, we get this thing, and immediately from this equation we can do a lot of simplification. You know what we can do? We can differentiate with respect to x. So, we get del x and this is square, this is square, differentiate with respect to y, differentiate with respect to z. So, your this thing would become like this. Now, similarly in this guy we can differentiate with respect to time. So, this would become square, square, square and del t, del t and del t. So, you know what will happen now is that this term, this term, this term would, you know, from these are the equations we can just transpose each of the terms underlined here on the right hand side and substitute for the underlined terms here. So, once we do that, we will get 1 by C naught square times del square P by del T square is equal to your remember there was a minus sign here. So, we will get minus here. So, minus can be transposed on the other side to get your this thing. So, we will get Laplacian. Your familiar wave equation in full 3 dimensional coordinates, where del square is nothing but the Laplacian operator in 3-dimensional Cartesian coordinate system, remember. So, we have finally arrived at the 3-dimensional wave equation, but without a flow. Now, we can easily convert this to your wave equation by insisting that P pressure field, acoustic pressure field now is your x, y, z, e, j, omega t. Okay. So, once you do that, you get minus omega square. Okay. So, minus omega square by c square, or omega by c is k naught. So, what it would mean, del square plus k naught square whole operating upon p is equal to 0. Okay. So, this is your much sought after Helmholtz equation in 3D coordinate. Let me expand this out completely for you. So, we get this equation. So, finally, this is the result that we are waiting for a long time. Now, we can actually cleverly guess what will happen before we move on. From here, there are lots of things that we could do. One thing that will come to our mind is obviously to go ahead and solve, get the variable separate form. If you can analyze from your get back to your engineering mathematics days, your undergraduate days, where we used to study the hyperbolic equations which are separable in separable coordinate system. Cartesian system is a coordinate system where solutions can be separated out in x, y, z coordinates, and then you can combine individual solutions and get the particular modal aspect, modal solution, and then expand it out completely in terms of Fourier series kind of a thing. So, well, that is pretty much what we will do here. So, one way is to actually go ahead and do the variable separate form. We will do that in this lecture. The other thing is, of course, include mean flow effects while retaining the Cartesian coordinate system. So, one way, because of lack of time, what I would do in this course, in this lecture here, as far as 3D things are concerned, just include the additional terms that would arise when flow u naught is there along the x direction, with the understanding that you guys will also have a look at the lecture from the last week. So, you can kind of relate to that. It's relatively straightforward, and then that equation is your Helmholtz equation in Cartesian system with flow along a certain direction. That is to say, the equation that governs wave propagation in a rectangular waveguide, but with mean flow along the axis of the duct. Then we can go ahead and impose the boundary conditions and all that. And the other thing is, of course, change the cross section. So, all this while we are worrying about the rectangular cross section, what we could do is that get the circular cross section as well, but we will probably sort of worry about that later, and then right now just focus on different cases of rigid walled rectangular ducts with or without mean flow. So, now let us quickly move ahead and talk about the additional terms that would be present when we consider the effects of mean flow. So, what are those? Let us quickly do that. So, then it will become your rho naught times del dot u plus d dt, that is substantial derivatives times rho is equal to 0, that is your continuity equation. So, if we basically expand this out, so what will we get? We will get del, or this is actually your vector, So, this we will get del x u tilde plus del v y, there is nothing but your old divergence operator, plus your remember what was d dt? What was d dt? It was nothing but del del t plus u naught times del del x, because we are assuming mean flow along the x direction. So, with that understanding, it would become, this is rho tilde. So, it would become your rho tilde t plus u naught times, okay. So, we will get this kind of a thing, okay. So, this is the continuity equation with flow along the x direction, but 3D continuity equation. Clearly, by setting u naught to 0, if we set this particular term to 0 u naught, we will get 0, we will get basically your get back the equation for without mean flow. Now, what is your momentum equation? Your momentum equation, considering the mean flow, the expanded out version u tilde is equal to plus your this thing, and the other equations will basically remain the same. So, this is your V plus y is equal to 0, and your rho naught times this is equal to 0. So, we can basically proceed ahead with differentiating with respect to your z, because eventually you would like to get the Laplacian. So, y and this is square, and so this we could we can simply transpose out your terms, this term here, this term here, and we can basically differentiate both the sides with respect to x. So, once we do that, the top equation u naught is mean flow velocity, which is constant in space and time. So, we will get basically nothing but this thing. Okay. We probably what we can do is sort of highlight out these terms, and we get this. We can now again go back to your continuity equation and differentiate with respect to time. So, once we do that, we get this square del t square del t, this is square square, and this will become square and del t. So, now as usual we what we can do is basically replace each of the underlined terms here, we can replace that with these particular quantities minus del square y del this thing, and this particular term del square u tilde and del x del t, all these terms, this particular thing as well as the other term del square rho, all this can be simplified further when we make use of this thing. For example, this particular term del square u tilde all this thing. So, this can be eventually be expressed in terms of the other variables, in where you have only derivative with respect to the space. So, all this term will be can be translated on the other side. So, we can replace eventually this particular term. Then possibly we need to basically worry about eliminating one of these, this particular term. So, that we can sort of easily do once, in fact, this rho tilde can be written as rho tilde is, as we know, is given by your p tilde by C naught square. So, even this term rho tilde can be eliminated and expressed in terms of p. So, all we will be left is basically del square u tilde by del x square, which we can again eliminate using the first order equation as we exactly did in the week 1 lecture. So, I am probably not going to show you those computations. I am just going to write down one final expression that will be valid when you combine the equations that are shown here on this slide, on the following slide here, into the Helmholtz equation incorporating the convective effects of mean flow, which when written in a little compact manner is given by your this thing. This is operating upon p or p tilde, as you can say, where del square is your this thing, your 3-dimensional operator or the Laplacian, and d dt, as we already know, incorporates the convective effects of mean flow, and that is given by your d dt is your del t, partial derivative with respect to the time, and the mean flow u naught, which is along the z direction. So, now basically now if you expand this out, it is a bit tedious and we can get to it, and so d dt this square would mean this operating on something. What it means is okay, and this then further operates on each of the quantities. operates on this plus ddt of u naught I can take out, and this further operates on this thing. So, if we go to the next slide to simplify matters, let me work out the algebra a little quickly. So, this is your this operator, so this when you multiply this out is del square plus u naught times del square del z t plus u naught times del square del t del z u naught square times. So, this will happen, and then what we will get is basically your familiar term which we saw in the first lecture of this week, or probably the second lecture I reckon. So, this thing. Finally, so this is your operator. Once we substitute this guy in the above equation, once we substitute this guy in this particular equation, we will get the fully expanded out form. So, that would be your del square p tilde del square t plus 2 u del square by del z t plus u naught square times del z square, and so it's minus c naught square times so we can finally put it in a more formal form. What we could do is simplify the algebra to get the following. This will become 1 minus m naught square minus 2 by u c naught square. This is exactly what we saw a few lectures back for the one dimensional case, and so this also occurs in your 3D case. So, this is the final form, and of course, once we insist on sort of time harmonicity, let us do that. Let us assume the harmonic response, that is your p x y z e j omega t. So, once we put that sort of a thing, what we will get is your minus 2, this becomes m naught and it's j omega. So, here is omega, omega by c is c naught, and we will get first order damping sort of a term plus k naught square p operating upon 0. We will get this term. This is your equation with including the convective effects of mean flow and considers 3-dimensional propagation. So, this is really the expanded out version of the more condensed version that was presented just a while back. So, clearly we can see when m is 0, it reduces back to the original case when there is no flow. Now, we have derived this equation without really going into the control volume, at least for this case, but we did it for the case of a 0 mean flow. Now, it basically our job to find out the modal solutions. So, the way that we will follow, the procedure that we will follow is basically to find out the modal solutions in terms of m naught, that is for the rectangular waveguide, infinite rectangular waveguide carrying a mean flow say along the positive z direction. So, it will involve the modal solution will involve terms which has m naught or dependence on the Mach number, small Mach number, and for the more special case of m naught 0, we can get the case of a rectangular waveguide with 0 mean flow, and here of course we are considering a rigid wall waveguide. So, we will learn how to employ the rigid wall boundary conditions. So, this is clearly a equation that can be separated in the in the 3 orthogonal directions x, y, z. This is in a separable coordinate system. So, what we really need to do is that assume p is equal to x of x, y of y, z of z. So, once we do that, I am sort of omitting the algebra and just directly writing the stuff here, and here is 1 minus m naught square, and you will get your z dash divided by z and plus k naught square is equal to 0. So, you can assume this particular guy is kx square, and same thing can be done with this thing. This can be minus ky square. Okay. Now, there is clearly no flow along the x and y directions, but we want basically a solution that is bounded, and it is obviously not 0. Clearly, if kx is 0, then we get sort of trivial solutions. We are not sort of interested in that or things like that. And if variables, let us say this is lambda minus lambda, and if lambda happens to be negative here, or just if you can just consider this entire guy as lambda happens to be positive here, then we get one part is exponentially increasing, other part is exponentially decreasing. So, it is unstable, so it is spatially growing kind of a wave, that is not permissible. So, what we would do basically is that we will assume kx is real number and kx square would be also be real, and then minus kx square would be always be negative. So, once we insist on such kind of a variation for x and y directions, what we will get is basically x dash plus kx square on x is 0, same thing for y. We get these two equations. Okay. If we assume a solution of e to the power mx, here x is something like this, and what we do is that we substitute this guy here, we get m square plus kx square is equal to 0, or we can probably say mx or probably just m, and same thing for n square plus ky square is equal to 0, leading. Now, remember kx is real, so m is nothing but plus minus kx, I kx, and n is nothing but this kind of a thing. These are purely imaginary things. So, what does it mean? This means will become your C1 into e to the power minus I kx x plus C2 into e to the power I kx x. This can also be written in the form, let us say B1 into cos of kx x plus B2 into sine of kx x. Okay. And this similarly would be your this kind of a thing. So, now we have to employ the boundary condition. So, what does boundary condition mean? Basically, we have the pressure component along the x and y directions vary according to say equations 1 and 2. Okay. We know from our Euler equations this is something like this. So, we will get your pressure something like this. Clearly, this is a partial derivative. So, the other components of the pressure, the y component as well as the z component shouldn't really bother us. So, whatever their forms are, we just probably would be interested in the x part. So, that would probably we have to take a derivative of your x function. So, once you do that, what will we get? We will get your b times this is kx and cos this becomes sine sin kx x, and here you have a minus sitting, okay, and b2 times kx cos kx like this. Now we need to simplify this thing further. Kx obviously we have taken out, and let me take minus kx out. So, this will become like this, b1 times sin of kx x and minus b2 times cos of kx x. So, now x is equal to 0. Now, if you remember, our cross section was something like this, x y. So, this is 0, this was, say, let me call this as breadth is b, height is h. So, now once we simplify, what are our boundary conditions? At x is equal to 0, that is here, we have velocity is 0, that is on this plane. Similarly, on this plane we have also velocity 0, which is your u x is equal to b. Okay. So, under such conditions, once we put this kind of a thing, we will get b1 is equal to b1 into 0 minus b2 is equal to 0, is not it? That would mean that this term of course is not there, and b2 is 0, and other condition that follows. So, b2 is not there. So, now other condition is invoking this particular guy, and we will see b1 into sin of kx into L, that is equal to 0. So, that would mean sin of kl is equal to sin of n pi, or yeah, it can be n pi, where n ranges from 0, 1, 2, 3, 4 like this. So, that would mean kx L is equal to n pi, kx is equal to n pi by L, where n ranges from 0, of course, will give you a trivial solution, or probably we can consider that in 0, 1, 2, 3. It is not quite trivial in the sense that when you put kx is equal to 0, so n is equal to 0, that means kx, the wave number along that direction for the lowest order mode, that is 0, but still you will have wave propagation, and we will see this is a special case when n is 0, when n is 0. Now, in a similar manner, if you do the same exercise along the y direction, we will eventually end up getting something like this. So, this is I made a small mistake, I guess. So, I think it was something like this is b, because that is what we agreed upon, and this was also b, and remember our height of the duct was h. So, we will get m is equal to 0, 1, 2, 3 like this. So, this is again a special case, and we will see why it is special. Now, after having derived the wave numbers k x and ky, so these are the transverse wave numbers, or the wave numbers along the x and y directions respectively, and they signify higher order modes. So, once we let me just write down the x component of the solution. So, remember b2, based on this condition, b2 was 0, and similarly we can also get that b4 is 0. So, eventually we are getting solutions in terms of cos or cosines, not sines, for a rigid wall duct. That is, here we have a rigid wall condition, or velocity, normal velocity 0 along perpendicular direction. Soft wall, in a hypothetical case, or in a lining, highly absorbent lining, that will set pressure to 0. So, we will get sines in terms of cos. Wave numbers would be also different. So, here we are getting something like, let me, if I were to combine the solution, let me write down something like this. So, this will be, say, some constant, say Cmn cos of I think it was n pi b into cos of m pi h. Okay. This was it, where m and n range from 0, 1, 2, 3, 4. Now, we have this kind of a thing. Now, the thing is that if we go back to our this equation, the moment we agreed on separating the variables. Okay. If we put minus kx minus ky square here, and let us assume that this guy, let me use another color, this is minus kz, wave number along the z direction or the propagation. Remember, in the 1D case, the underlying this term and this term were not there, and of course the other terms are there when you have a mean flow. Now suppose you set mean flow to 0, m naught is 0. Okay. So it is clearly evident that for the simple case of no mean flow and one dimensional propagation, simplest as it can get, kx or kz square was equal to k naught square, or kz is equal to plus minus k naught, that is waves propagating along the positive z direction and negative z directions respectively. Okay.